Hello, in this video we're going to derive the correlation of a discrete bivariate distribution, and this is the distribution function. It's f of x is equal to 2 over n times n plus 1, where y goes from 1 to x and x goes from 1 to n. So let's just start. We need the marginal of x, which means we sum over y of our joint distribution, which is this. So since this is a constant in regards to y, it can be taken out front the summation and we're left with 1. So now we're summing 1 from 1 to x, which is x. So we get 2x times n over n plus 1, and x goes from 1 to n. Let's look at the expected value of x. So that says stick in an x to the PDF of x. So the constant piece comes out front, and then we get x times x, which is x squared. And now I have a video called Summation Formulas for Integers on how to derive the formulas for the sum of, say, x, or the sum of x squared, or the sum of x cubed. And so I'm going to default to that video and just show you the formula. And in that video I derive them. It's a pretty cool video. So then this simplifies to 2n plus 1. If we look at the expected value of x squared, or the second moment, we take out the constant pieces here from the sum, and we take x squared times x, which is x cubed. And so this is the sum from 1 to n of x cubed. And again, I show you how to derive that formula, which is this. And then those simplify to n times n plus 1 over 2. Now let's look at the variance of x squared, which is expected value of x squared minus expected value of y quantity squared. So you plug in the pieces that we just calculated, simplify it, and we get this. Now we need to do the same thing for y. So let's find the marginal distribution of y. So we sum over x, and x goes from y to n. And I'll show you that in a second why that's the case. Let's assume it's true for now of our joint distribution. So we take out the constant and we sum from y to n of 1. So let's just add up however many terms there are, and that's n plus 1 minus y. So this is the marginal distribution of y. So now let's look at why x goes from y to n. Now if you remember, y goes from 1 to x and x goes from 1 to n. So that says that, let's say x is 3, then y takes on 1, 2, 3. When x is 5, y can take on 1, 2, 3, 4, 5. And so our bivariate distribution is triangular here. So when we sum out x, let me rephrase that, when we were looking at the marginal of x, we summed out y. So we sum this way. So we go from 1 to x. This is the y equal x line. So we go from 1 to x, and that's what we summed out. But now when we sum out x, we have to go from y to n. And so this is why we sum from y to n. It's because that's the way our bivariate density, or of discrete type, works. So now the expected value is we stick in a y times our PDF. And so the constant comes out front, and it's y times this piece here. Now we think of this, I'm going to break it up into two. This n plus 1 and y. So it's going to, the n plus 1 comes out, and that's what this is. And then we're summing y from 1 to n. And here, it's minus y squared, and we still have the constants out front. And again, summation formulas for integers, I'm going to pass to that. So that becomes this. This becomes that. Constants are still, we get some cancellation there. And then it reduces to n plus 2 divided by 3. Now let's look at the expected value of y squared. Stick in y squared in the PDF. Bring the constants out. And again, we're going to think of it as two formulas. We're going to sum this and then sum that. And so the n plus 1's come out, and we're left with 2n, but then we just have y squared and then over here we have minus y cubed. So that becomes this formula, y cubed becomes this formula, add them together, we get this. Now the variance of x, I'm not for sure why I rewrote it, but that's what we calculated on the previous page. The variance of y is the expected value of y squared minus, expected value of y quantity squared. So expected value of y squared we put there minus, the mean squared, and it reduces to this. And actually, maybe I put them back to back because they end up being the same variance, which is going to help us when we calculate the correlation. Now, to calculate correlation, we need the covariance. And to calculate the covariance, we need the expected value of xy. So that means we stick in xy times our PDF, which is this. Those come out as constants. So the x here we can take in front because it's constant in regards to y, so we get this. Well, this is a summation formula, which is this, and then we here the 2's cancel and we get x cubed plus x squared, which is this, and then we, that is this formula, this is this formula, and then it all simplifies to this. So now to calculate the covariance, we use this formula here, and we plug in the pieces that we calculated before, and then that all reduces to this quantity. Now the correlation is the covariance over the product of the variances, the square root of the product of variances. Now these are the same thing, so it's like squared, but then you take the square root, you just get it back, and the covariance we just calculated, so when you take the reciprocal and multiply, you get 1/2. So the correlation between these two variables is 1/2. Now, that's what the video promised, but as I was going through this, I'm like, let's look at conditional probabilities. Maybe that'll be informative. And there is one piece below that I think you'll find it interesting. So now if we look at the conditional of x given y, and I guess technically that should be equal to little x, but I didn't write it like that. So we have the union, or the intersection over the marginal, and this right here, is given in the first page, first line is this. The marginal we calculated to be that. This simplifies to 1 over n plus 1 minus y, and x goes from y to n. Now, to calculate the expected value of x given y, we stick in an x right here. So this is a constant, it gets pulled out, and we're deriving this. And the formula for this is, since it's linear, it's n plus y, which is that, times however many there are, and it's n plus 1 minus y, so that's this, divided by 2. So that's that summation formula. This simplifies to n plus y over 2. Now, out of curiosity, we've all seen the formula, expected value of x is equal to the expected value of the expected value of x given y. And let's calculate that to see if we get the same thing. Now, one subtlety, this right here, we're integrating out x, so there's no x's in this formula, so it's a function of y. And now we're going to use what's called LOTUS, and look that up, LOTUS for statisticians. Actually, lazy, otherwise, unknown, I forget what it even stands for, but look up LOTUS statistician, where we don't have to actually have the distribution of this function, but because it's a function of y, we only need the distribution of y. So it says stick this value and take it times the function of y, and we get this. And here we just calculated as that, and the marginal of y was this. So we're going to sum over that. We take out the constants, which is what we do here, and we have this piece. Now we multiply this out and we get this, and then we take the sum through each of those, and we get those cancel, we get n, we get 1/2 here, and then we get minus n plus 1, and those add to 2n plus 1. And notice this is exactly the mean that we calculated from first principles of the expected value of y. So it's kind of neat that this formula does work. And that's actually one of the main reasons why I kept going in this video, is to show you that piece there. But now let's do it for the f of y given x. So here we need to plug in the pieces of information we know here. The bivariate distribution was given on page 1. The marginal of x is this, which we already calculated. That simplifies to 1 over x. And y goes from 1 to x. So the expected value of y given x is we stick in a y with this this PDF, and then sum over y. Well, the x comes out front, and then the sum from 1 to x is this. Simplifies, we get x plus 1 over 2. So that's the expected value of y given x. So now let's do this formula. The expected value of y is the expected value of this quantity. And this is a function of x. So we take this, which is expected value of y, times the marginal of x, which was this we calculated on the previous page. Now take out the constants, the 2's cancel, and we're summing x squared and x. Those get passed to here, multiplied out, we get n plus 2 over 3, which is the exact quantity that we got for the expected value of y on the previous page. Well, that's all I have for today. Hope you enjoyed it. Please like it if you did, and subscribe so you don't miss the next one. Thanks. Bye.